This is a video lesson for Newton's second law. The learning target for this lesson is, I am learning to describe the conditions under which a system's velocity changes. The success criteria for this lesson are, I can understand that the force acting on an object is equal to the object's mass times its acceleration. I can understand that increasing an object's mass will decrease its acceleration. And I can understand that changing an object's acceleration requires a change to the force being exerted on the object. Okay, so what does Newton's second law tell us? So here we have the equation version of Newton's second law. So we have sigma F, which is the sum of forces. We've seen this before. M is equal to mass, and A is the acceleration, where acceleration is equal to the change of velocity over time. So basically, Newton's second law talks about how the sum of forces acting on an object is equal to the mass of that object, or the mass of the set of objects, times the acceleration. So the amount of force acting on an object determines the acceleration that that object has. So we can manipulate the equation for Newton's second law to give us different bits of information. So here is the law as we looked at it last time. The sum of forces is equal to mass times acceleration. We can solve the equation for acceleration as well. So here we have acceleration is equal to the sum of forces divided by mass, which we can also think about as the acceleration is equal to the net force divided by mass. Or if we solve for mass, we can say that mass is equal to the sum of forces divided by the acceleration. So we can see some different relationships here. So if we look at acceleration, we can see that the sum of forces divided by mass. So as mass increases, acceleration is going to decrease, assuming that the force stays the same. If we want the acceleration to stay the same, when mass increases, the force has to increase, or the net force has to increase, or the sum of forces have to increase. Similarly, if the mass is staying the same and we want the acceleration to increase, then we need to increase the force. Okay, let's look at some examples of using Newton's second law to solve problems. So this is example 1, acceleration versus time graph. So a spacecraft in deep space fires its thruster, which ejects fuel from the spacecraft. The ejected fuel exerts a constant force on the spacecraft, and the total mass of the spacecraft decreases at a constant rate. Which of the following graphs best represent the acceleration of the spacecraft as a function of time while the thruster is firing? Okay, so we're looking for an acceleration versus time graph that matches this situation. So we have our equations for acceleration over here on the right side. So we have acceleration is equal to the sum of forces divided by mass, or the net force divided by mass. So notice that as the mass decreases, as this number on the bottom of the numerator or the denominator gets smaller, so as this number gets smaller, the acceleration increases, assuming that the force just stays the same. So we can tell right away that we're not going to have a constant acceleration, and we're not going to have a negative acceleration, because the mass is going to get smaller as we go, which means that this whole fraction is getting bigger, so the acceleration is going to get bigger. So the question then is the acceleration going to increase really fast and then level out, or is it going to increase slowly and then get faster as it goes? So as this number gets smaller and smaller, the acceleration is going to get faster and faster. So this first option is not correct. The second option is our correct choice here. This is true because if you think about this number here getting smaller and smaller, think about it as a fraction. So we start with a whole number. So we start with, let's say, 4, then it goes to 3, then it goes to 2, then it goes to 1. Then it becomes fractions. So let's say it starts as a large portion of the total mass. So let's say it's 7/8 of a whole mass, and then it goes down to 6/8 and so on. Eventually it gets down to 1/8. When you're dealing with fractions, you're going to flip the fraction and multiply it. So you end up with the total force multiplied by the numerator, or by the denominator, and then divided by the numerator. So your acceleration is going to start. It's going to be getting bigger slowly, and then as you get less and less mass, it's just going to start taking off like that. Okay. Okay, example number 2, finding net force. So a system consists of 2 identical blocks connected by a rod of negligible mass. At the instant shown, the velocity of the center of mass is 0. So we have velocity 0, and the system has a non-zero acceleration to the right. Which of the following statements must be true? So A, the net force on the system is 0. B, the net force on the right block is greater than the net force on the left block. C, there is a net force exerted on the system directed to the left. And D, there's a net force exerted on the system directed to the right. Okay, so let's think about what's going on here. So we have these 2 identical blocks that are connected by a rod of negligible mass. So the 2 blocks are essentially connected to each other without any mass. And the whole system starts with a velocity of 0. So we have an initial velocity for the center of mass of 0 meters per second. And the whole system has a non-zero acceleration. So the acceleration of the center of mass is non-zero. So we have a non-zero acceleration. Okay, so the net force on the system is 0. This is answer choice A. This cannot be true because we have a non-zero acceleration. So to have an acceleration at all, we have to have a non-zero net force. So the net force on the right block is greater than the net force on the left block. Well, this cannot be true because the blocks are connected by this rod, and the rod itself has no mass, and there's no friction involved in the system. So if the right block has a force on it, the left block is going to follow along. So C, there is a net force exerted on the system directed to the left. Well, the acceleration we know is to the right. So since we have an acceleration to the right, we have to have a force that's directed to the right. So C is incorrect, and our correct answer then is D. All right, example number 3, finding acceleration. So we have a block of mass 3 kilograms, initially at rest, is pulled along a frictionless horizontal surface with a force shown as a function of time, t, by the graph at left. The acceleration of the block at t equals 2 seconds is, okay, so we are given a force versus time graph here, and we want to figure out the acceleration of the block. So acceleration is equal to question mark. Okay, so we have our equation written up here. Acceleration is equal to the net force divided by mass. So we need to figure out the force at 2 seconds. So if we look at our force versus time graph here, at 2 seconds, our force is 4 newtons. So using our acceleration equation, we have the net force is going to be 4 newtons divided by our mass, which is 3 kilograms. So at 2 seconds, our acceleration is going to be 1.33 meters per second squared. Okay, so what did we learn in this lesson? So we learned about Newton's second law. The sum of forces, which is also equal to the net force, is equal to the mass times the acceleration of an object. So if we increase mass, we decrease acceleration. So increasing an object's mass and leaving the force the same means that the acceleration will decrease. Lastly, increasing force increases acceleration. So if mass stays the same and force increases, the acceleration will increase. All right, thanks everybody.